It's time for the Harmonic Series. That series has a name. This infinite series, the sum of the reciprocals of the positive whole numbers, is called the Harmonic Series. I want to know if that series diverges or converges. And the first thing to do is to look at the limit of the terms. The nth term of the harmonic series is 1 over n. So if I take the limit as n goes to infinity of the nth term, well, what's the limit of 1 over n as n goes to infinity? This is 0. And what did the limit test say? The limit test tells us that if the limit of the nth term of some series is not equal to 0, then the series diverges. But when the limit is equal to 0, So in this case, the limit of the terms is 0 and the limit test is silent. At this point, we still don't know whether the harmonic series converges or diverges. Well, I can start adding up a bunch of terms. 1 plus a half, the first two terms in the harmonic series, is 3 halves. If I add the next term to the harmonic series, 1 plus a half plus a third, that's 11 sixths. And I could add the next term on the harmonic series, 1 plus a half plus a third plus a fourth. Well, that's 25 twelfths. I could add the next term in the harmonic series, 1 plus a half plus a third plus a fourth plus a fifth. That's 137 sixtieths. And I could keep going like this. If I add the first 10 terms together, 1 half, third, fourth, and so on up to 1/10, I get a number that's just under 3. Let's add up even more terms. So instead of just 10 terms, I'll add up the first 100 terms, and I'll get a number 5.187 or so. The question is, what happens when I add up more and more terms in this series? Even more terms. Well, if I add up the first 1,000 terms, I get a number that's about 7.485. If I add up the first 10,000 terms, I get a number that's just under 10. We're adding up a ton of terms, and still, the partial sums just aren't that big. Let's take a different approach. Here, I've started writing out the harmonic series, right? 1 plus a half plus a third. I've written down the first 32 terms of the harmonic series, and of course, it keeps going. I'm going to group the terms in a clever way. Well, I'll set aside the 1 and this first 1/2, and then I'll put these next two terms together, the third and the fourth, and I'll put these next 4 terms together, a fifth plus a sixth plus a seventh plus an eighth. Then I'll put these next 8 terms together, the terms between a 9th and a 16th, and I'll put these next 16 terms together between a 17th and a 32nd, and so on. Now let's underestimate each of these groups. I can underestimate 1/3 by replacing 1/3 with something smaller than 1/3, like 1/4. 1/4 is smaller than 1/3. I can underestimate a fifth, a sixth, and a seventh by replacing each of those with something smaller than a fifth, a sixth, and a seventh. Well, an eighth is smaller than a fifth, an eighth is smaller than a sixth, and an eighth is smaller than a seventh. Why is this a good idea? Well, here I've got 2/4, and 2/4 is a half. And that means a third plus a fourth, if I add those together, is at least a half. Here I've got 4/8. 4/8 is also a half. And that means a fifth plus a sixth plus a seventh plus an eighth, which is bigger than an eighth plus an eighth plus an eighth plus an eighth. A fifth plus a sixth plus a seventh plus an eighth must be bigger than 4/8. It must be bigger than 1/2. Now I've got 8 more terms here, starting at a 9th and ending at a 16th. Each of these terms can be underestimated by a 16th, right? A 9th is bigger than a 16th. A 10th is bigger than a 16th. An 11th is bigger than a 16th. A 12th is bigger than a 16th. All of these terms are bigger than a 16th. But now I've got 8 16ths, and that means a 9th plus a 10th plus a 16th. All of these together must be at least 8 16ths, and 8 16ths is 1/2. So if I add up these 8 terms in the harmonic series, I get at least a half. Now the next 16 terms in the harmonic series are each at least a 32nd. But if I add up 16 terms, each of which is at least a 32nd, That's an answer which is at least 1/2. The next 32 terms in the harmonic series, starting at 1/33 and ending at 1/64, those 32 terms are each at least a 64th. But 32/64 is a half, and that means the sum of the next 32 terms in the harmonic series is at least a half. The next 64 terms in the harmonic series, starting at a 65th and ending at 1/128, those 64 terms added up is at least 64 128ths. It's at least 1/2. So when I'm adding up the harmonic series, I can underestimate the answer by adding 1 plus a half, 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 and so on. So summing the harmonic series is even worse than adding up a half and a half and a half and a half. All of that is to say, the harmonic series diverges. Let's summarize this. The harmonic series diverges even though the size of the terms gets very small, even though the limit of the nth term is 0. And this isn't a contradiction. The fact that we know is that if a series converges, then the limit of the nth term is 0. But just because the limit of the nth term is 0 doesn't mean the series converges. The harmonic series is a great example of this phenomena, where the limit of the nth term is 0, but the series nevertheless diverges.